Hi, I'm Jack Buffington for HACKADAY.com. Today we're going to talk about pulse width modulation, and then we're going to implement it on the Pololu 3Pi robot. This is part 3 of our series where we're using this robot as a fancy development board for the Atmel AT-Mega 328P. Let's get started. Let's look at what pulse width modulation actually is. Let's say we have a motor or something that we want to turn at a certain speed. Now, with a digital device, we have full on or off, and those are our only choices. So if we have that connected, say with a MOSFET to the lead of a motor, it can be either full on or full off, unless we do something called pulse width modulation. What pulse width modulation does is you rapidly switch on and off whatever it is you're controlling, and the average of the on time versus the off time is what the device may see. So if it's a motor that has inductance, it actually sees an average voltage. If it's an LED that can blink on and off at millions of times a second, it's your eye that's doing the integrating of that. So that LED might actually be blinking on and off and really doing it, but your eye smooths all that out for you. So there's several different ways that you can do pulse width modulation. The first is you break up a slot of time into subslots like this, and during each slot you say, okay, well, if I want it to be half on, it might be off for half of the time, then on for half of the time. So the average of this is halfway. If you wanted it to be 3/4 on, just like something like that. So it's on for 3/4 of the time and off, and the average will be up here then, if this is an analog voltage. And so on and so forth. You know, mostly off, be like that. The average would be way down here. That is a way that you can control a motor if you're controlling it. Let's say you have the motor set up so that one end is on ground and the other one is getting its pulse width modulation. You can control the speed of that motor in only one direction, but you can do it in this manner, which I believe is called sine magnitude. Now, you could also do sine magnitude if you had, say, 2 pins that could pulse width modulate, and that could go into what's called an H bridge, and you could control the direction by pulsing one direction a whole bunch, and then when that's off, the motor is getting no power, it could coast, and then when you pulse the other one, it would go into the other lead. That's another way. The way that I'm going to show today is called locked antiphase. Locked antiphase. And what this is you have 2 pulse width modulation signals, or it could be just one, and you use some sort of logic to invert it. So if we're doing 2, which is what I'm actually doing on the 3Pi robot, the signals are going to look like this. They'll be completely opposite of each other. And this goes into the H bridge, and what it does is it causes the motor, if this motor could actually keep up with the speed that we're doing, it'll rotate a little bit this way, rotate a little bit this way. But since the inertia of the motor and the inductance in the motor is great enough, the end result is that if it's like this and they're even, it'll just stay put, and you'll hear the motor whining with a high-pitched noise. Now if I did it such that I had it so it might be like this, and the other signal is just opposite of that, what we get is, if the motor was super fast or had low inductance and no inertia, it would rotate for a while and go back, rotate for a while, go back. But because of the inertia and the inductance, what we get is just a constant speed in one direction. And if we alternated it so that this one was low a lot of the time, I guess that's not that clear now how I'm drawing it, but let's say it was low a lot of the time, it would rotate in the other direction, which is pretty neat. I have found that this method works better to drive a motor in open loop control. So when you're not getting any feedback about what this motor is doing back to your processor, if you drive it like this, you have a much more steady speed control than if you drove it like this. In this method, it tends to be that, I'll draw you a little graph of what it might be like. So this is the output speed. And what you're giving it. And let's see. Actually, I should have probably swapped this. But anyway, as your input, what you're requesting rises, initially the output speed will remain 0. And then it seems like the speed increases quite a lot. It's something like that. I've never actually graphed them compared to each other, but this is what it appears to be. At some point, maybe 10% on or something, then the motor will start turning and it'll start going. With the locked antiphase, it's much more linear. It's not totally linear. You're never going to get that unless you have a signal going back to the processor from, say, an encoder. But anyway, so those are two ways. I'll just talk about a couple more just because they're interesting. The first is called pulse frequency modulation, and it's a variant of pulse width modulation. What this one is we have pulses that are put out by the processor that are always the same width. And if they're spaced widely, like this, that averages out to a low value. If they're spaced close together, you get a higher value, and they can actually work out to be so that they actually, two pulses might happen one right after the other. So it would be like that. We end up with a high value. That's another strategy. One final one that I'm going to show you is, actually I have no idea what it's called, but this one's very useful if you are using interrupts to control your pulse width modulation, and you don't want to have it happen every cycle. So if you have a bit depth of 8 bits for your pulse width modulation, you don't necessarily want your interrupt to happen 256 times per cycle. That'll just suck up your processor power like crazy. So if you don't have hardware for pulse width modulation, here's one thing that you can do. Let's look at, let's say we're doing 4-bit pulse width modulation, and we want to do a value of 0, so 0 speed. That would correspond in binary to that. If we were doing 3, be like that. And just a quick refresher on binary. This one represents 1, 2, 4, and 8, like that. So if I were doing 5, it would be 4 and 1 would be on, and 11 would be 8 1 and 2, like that. Okay, now let's say that we check out this bit. That bit will correspond to a time slot that might be that wide, if this is time. This bit will correspond, because this bit is worth half of what this one is, it will correspond to a time slot that's 1/2 of the width of this one. And then this bit here will be worth half of this width. And finally, like that. So if I was doing a on time of 5 of 16, we would have this one would be off, this would be on, off, and on like that. That's a bit more of an advanced thing. I haven't told you guys about interrupts yet, but those are some strategies to do pulse width modulation. Today we're doing phase anti-lock modulation, and let's go back to our computer and take a look at what we need to know to actually pull that off on the ATmega 328P. On this processor, there is hardware that can control pulse width modulation, and it is controlled by 4 registers per, actually technically 3 registers per pulse width modulation that you want to get out. The first register that we'll be looking at is TCC R0. This is for, it's linked in with a timer. So we have timer 0, timer 1, and timer 2. So this is the timer counter control register for timer 0, and this is the A register for it. And what we need to do, and I may need to pop back and forth to my code here, which I hope I still have loaded. Looks like I do. Good. Okay. Let's just look at this first. This is the datasheet for the ATmega 328. And we've got a couple registers here. And actually, I should just follow on with what I'm doing here. Let's start with this. So this is the OCR0A, and that corresponds to the output compare register for timer 0, and then the A output. So there are 2 outputs that this pulse width modulator can do. It can do it on, I forget which pins. Yeah, I forget which pins. I'd have to look that up in the datasheet. But anyway, we're setting the match register to 128. So this means that the pulse width modulation will be on half of the time and off half of the time. And we're doing the same thing for the second pulse width modulation. Now we're looking at the timer counter control register 0A. We're going to set a few things in this. Now, I have broken it out in my code so that I am setting each bit individually. You don't necessarily have to do that. You could figure out what these bits add up to and say TCC R0A equals 92 or whatever that might be, and that would be just as good, but I'm just doing this to be a little bit more illustrative of what I'm doing. So I have set it to fast pulse width modulation mode, and it only counts up to 255. Counter 0 is a 8-bit counter, so that's the maximum that it could count up to. I am making the polarity for the A pin or the A output be normal, meaning if it should be high, it is high. And for the B pin, I have inverted it so that when the A pin is high, provided that I set both OCCR0A and OCCR0B to the same value, then this one will be inverted polarity from this one. And that was a little something that tripped me up when I was figuring this out, because I didn't realize that these were both locked into the, or that they weren't locked together, but they were controlled by separate registers. Anyway, that's inverted. And then I set the prescaler to 8. I think that's incorrect. I think I changed that and didn't change my comment. And then I do the same thing for the right motor, which I just copied all these and just changed it. So this is timer counter 2. We skipped the counter because timer counter 1 is a 16-bit counter, and that would work just fine for our pulse width modulation as well, but just to keep things simple, I wanted both to be the same number of bits, and more to the point, the 3Pi robot is connected up to those pins, so I should probably use them. Otherwise I'd have to do it in software, which is a pain. So I do the exact same thing for the other register. Now, when I want to set my speed, I have to set both of these to the same value. And if I set it higher than 128, which is the mid value for an 8-bit processor, if I set it higher, it'll rotate the wheel in one direction. And if I set it lower, it'll rotate in the other direction. And the farther I get away from 128, the faster that motor will be turning. And as you'll see here in a minute, it can be quite fast actually. I'm pretty impressed with this 3Pi robot speed, because so many of the projects that I've played around with in the past have been awfully slow. So I've created just a quick little routine to set the speeds of the motors. So I pass it the left motor and the right motor. And I've actually labeled it here. So higher numbers are going forward, lower numbers are backwards. The 3Pi is using differential steering. So it only has 2 drive wheels. And if I drive both motors forward, it goes forward. Both motors backwards, it goes backwards. And if I drive it in opposite directions, it turns. Alternately, you know, I could always keep one stopped and turn, but it's... Anyway. So all I have to do is pass to set PWMs the speeds that I want. And we'll just go back up into the top of my program. Got a little thing that prints HACKADAY on the LCD screen. I set the port D pins as outputs. I think that's a leftover from a previous program. I set up the PWM, which is that routine that we were just looking at. And then I've got it going forward, stopping, going backwards, stopping, turn, I believe, left, right, left, and then stop. So I have loaded the program into the robot, and let's just turn it on. The first thing that's going to happen is it'll print HACKADAY across the screen. It'll go forward, backwards, turn, turn, and then it's done. So as you can see, it's a pretty peppy little robot, and that wasn't nearly as fast as it can drive. As you might have heard, actually I'll do it again here. You can probably hear the whining. I'll bring it up by my microphone real, duck in there. You can hear that whining. That's because of the phase, or the lock antiphase pulse width modulation. If you were doing the other type, where it's sine magnitude, I believe is what it's called, you would not have that if it's stopped. But again, I did this because I feel that it gives you better precision. And let's say we wanted to do something like maze following or something like that, maze solving. You want to be able to make repeatable, nice turns, and this type of pulse width modulation will allow you to do that. So that was pulse width modulation and on the ATmega 328P processor. This is Jack Buffington for HACKADAY.com.